Now just see what is the meaning of this Archimedean property of real numbers. This says that the real number field is Archimedean. The real number field is Archimedean. That means if you are having two real numbers, A and B, they are any two positive real numbers, then there always exists a positive integer n such that n times A is greater than B. So this thing hold. This property says that whenever you are having two positive real numbers, you can always find an integer n such that n times one number is greater than the other number. And you can see with the help of an example, let's suppose we choose A to be half and B to be 3, right? You can always find a positive integer n. Let's suppose take n to be 4. So you can see 4 नहीं 6 की जगह भी 7 ले लो, right? So you can see n times A, 7 times half, clearly it is greater than the number B. And this thing always hold. You can always find a number n such that this thing hold. Now just see the proof. Again we will prove it by contradiction. So what is given to us? Given that A and B, they are the positive real numbers. So let A and B be two positive real numbers, and suppose that for all positive integers n, that your n times A is less than equal to B, right? So we will prove it by contradiction. So on the contrary, we assume that for these two real numbers, this thing hold, n times A is less than equal to B, and this is true for every positive integer n. Here we are saying there exists only one, at least one positive integer n such that this thing hold. So on the contrary, we assume that this is true for every positive integer n, that your n A is less than equals to B. Next we consider a set S. So we consider a set S of n times A numbers where your n is a positive integer. Now clearly this set is bounded from above. Why? Because हमने assume किया your NA is less than equal to B, where B is any real number, positive real number. So clearly this set is bound by B. Or you can say B will become the upper bound for the set S. Is this point clear?
Yes, sir.
So we consider a set S as a member of NA, n times A, where n is a positive integer, and clearly this set is bounded from above by the upper bound B. Now by the completeness property, by completeness of ordered field of real numbers, set S must have supremum. In real number, say it is capital m. Now since your set S, it is bounded from above, so by the completeness property of ordered field of real numbers, S must have supremum in R. Is this point clear?
Yes, ma'am.
Now supremum means what? Every element of the set S is less than equal to capital M, and this is true for every n belonging to integers, positive integers. Right? Every element of the set S is clearly less than equal to capital M. Every element of S is of the form n times A, where n is integer. So that means n times A will be less than equal to capital M for all n belonging to the positive integer. Now since it is true for all n belonging to the positive integer, it means it should be true for n plus 1 times A less than equal to M. अगर सभी पॉजिटिव इंटीजर्स के लिए ट्रू है, whatever you put the value of n over here as a positive integer, this is always less than equal to capital M, then clearly n plus 1 times A is also less than equal to M. Is this point clear?
Yes, ma'am.
No, which further implies that NA plus A is less than equal to M, or which further implies NA is less than equal to M minus A. And this is true for every n belonging to the positive integer. So what will you have? You have that M minus A is an upper bound for the set S.
Yes.
But is it possible?
No.
Ma'am.
This implies M minus A is an upper bound of the set S. But M minus A is clearly strictly less than M because your A is positive number, which contradicts the assumption that capital M is the least upper bound of the set S. Right? So hence our supposition is wrong. That is, there always exists a positive integer n such that n times A is greater than B. So whenever your A and B, they are positive two real numbers, two positive real numbers, then there always exists a positive integer n such that this thing holds. Is it clear to all of you?
Yes, ma'am.
Now, based on this theorem, we have some corollaries. Now, just see the first corollary. If your A is positive real number and B any real number, then also there exists a positive integer n such that your n times A is greater than B. Now, how to prove this? Here A is any positive real number, but B that may be negative, that may be positive. So we have two cases. First, your B is positive real number, and secondly, B is less than equal to 0. Okay. So if your B is strictly greater than 0, Then by using the previous theorem, you get a positive integer n such that this thing hold. You can apply the previous theorem, because in that case you will have two positive real numbers. So by using the Archimedean property, we have there always exists a positive integer n such that this thing hold. Is it clear?
Yes, ma'am.
So case left when your b is negative, when your b is less than equal to 0. And this will true trivially. And every negative real number or 0 number is always less than a positive number. So this hold automatically. This is your positive number and this is negative or 0. Clearly this number will be strictly greater than this. Is it clear?
Yes, ma'am.
So whenever your b is less than equal to 0, the result holds trivially, because this thing hold trivially, right? So if you are having this theorem, you can prove the previous one, and you can consider this case that whenever your b is negative, we know that negative number is always less than the positive number. So this thing hold automatically, right? Now see the next corollary. This says that for any positive real number a, there exists a positive integer n such that n is greater than a. Now, how will you prove this? By using the Archimedean result. How will you prove this? So here in particular, you can put a to be 1 and b to be a in the previous result. मेन रिजल्ट जो है आपका, उसमें a को 1 पुट करो, b को a पुट करो. आ गया आपके पास यही प्रूफ करना है आपने. Here if you choose this to be 1 and this to be a, so you will have there exists a positive integer n such that n is greater than a. Is it clear?
Yes, ma'am.
So that is the particular case of this theorem, right? So in particular, if you choose a to be 1, this is clearly positive real number, and by choosing a to be b, because already हमें given है a positive real number है, so by using that theorem we have n is strictly greater than a.